Good morning, all, and welcome to the session on overview of classification and regression models. Before we understand the models, let us see what is machine learning. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. Let's look at a more technical definition of machine learning. A computer program is said to learn from its experience given by E with respect to some task given by T and some performance measure denoted by P. If its performance on T, as measured by P, improves with the experience E. Looks like complicated, but it's easy. Let's go through an example to understand this. Let's say our objective is to build a spam filter. So the experience E is nothing but the training examples that help us to learn. So you all know that when we are doing machine learning, we have to divide our data set into training as well as test data set. So experience is built on the training examples. The task T is nothing but when our classifier, our filter is able to figure out the spam mails from your non-spam mails. Performance. Obviously, when we have built our spam filter, we need to see whether it is rightly classifying our spam and non-spam mails. And this is what is the meaning of performance measurement. It is nothing but the ratio of correctly classified emails. Once we have an understanding of what is machine learning, let us see the types of machine learning algorithms. Basically, it can be divided into three categories: supervised, unsupervised, and reinforcement machine learning. Here, the focus is on building model, and usually supervised learning techniques are used primarily to build models. So, the focus of this presentation is going to be on the supervised learning techniques. Let us understand the meaning of supervised learning. So, as we know, supervised means somebody is observing. It's a sort of a learner where the teacher is there. So, what do we mean by this? Here, the data set that is there is labeled. That means we have the input features and we have the output label. So, the learning is happening with respect to the input feature for the corresponding output label. And that is why this technique is called as supervised learning technique. Primarily, it can be categorized into regression based technique or classification. So, what is the difference between regression and classification? Classification involves the output in terms of specific categories. That could be yes and no, true, false, 0, 1. For the example that I gave you, building a spam filter, the output is yes, it's a spam mail. No, it's not a spam mail. So output is in terms of the classes. There is where we have classification based models. Regression. When we are looking at the output in terms of real numbers, then it is regression based learning. For example, I want to forecast the price, the stock price of a particular stock. So it's a real number, the value of the price, and that is why it is called as regression based technique. Now, let me list down few important supervised machine learning algorithms. Categories are classification and regression. As you see, linear regression is the first technique under the head of regression based technique. So obviously the output is in terms of a real number. Now linear regression technique has drawback. To overcome these drawbacks, regularization techniques in forms of lasso and ridge regression are being applied. So all these three techniques fall under the umbrella of regression based techniques. Logistic regression and naive-Bayes classifier are two simple classification-based algorithms. If we look at decision tree, support vector machine, ensemble-based techniques, and artificial neural network, all these four techniques can either be used to solve a classification problem or a regression problem. Now, let us have a detailed understanding or overview of these techniques. Let's start with linear regression. It's one of the most well-known models, but please remember, it can only be used when there exists a linear relationship between the input variables and the output variable. If there is a nonlinear relationship between the variables, then this model is not going to be a good model for our data set. Advantage of this model is very easy to understand and interpret. The disadvantage includes it's very prone to overfitting. It does not work well in case of multicollinearity. So if two input features are connected to each other, then we say that there is the existence of multicollinearity. As I already mentioned, if there is a nonlinear relationship existing between independent features and dependent variable, this technique should not be considered. Python implementation is given in this slide. Please remember, there are many packages that support machine learning. sklearn is one of them. So here we have the function linear regression, which can be used to create a linear regression model. Let's go to the second technique, the logistic regression. We have the word regression, so you must be assuming that again the output will be in terms of real numbers. But no, here the output is in terms of the classes. So please remember, we use logistic regression when our dependent variable is not continuous. Now, three types of logistic regression can be defined: binary, multinomial, and ordinary logistic regression. Binary logistic regression is used when we have two outcomes. For example, spam filter, yes or no. Person has a disease, yes or no. 0 or 1. So when we have two output classes, we use binary logistic regression. Multinomial logistic regression. When we have more than two output classes, then multinomial logistic regression is used. When we have more than two output classes, but the order matters, then ordinal logistic regression is used. This is mainly used when we have a ranking. For example, we all see the Likert scale. We all see the ratings provided by the users on various e-commerce websites. So 1 might be low and 5 might be high. So order is what is to be preserved and maintained. And in that case, we make use of ordinal logistic regression. Python implementation of the same is being shown on the screen. Now, let's come to another technique called a support vector machine. Very popular and can be used for both classification as well as regression. The idea here is there is a hyperplane that separates the different classes. So, how do we define the hyperplane? A kernel function is used to define this hyperplane. There are four types of the kernel functions that are being defined: linear, polynomial, radial basis function, also called as RBF, and sigmoid. So linear kernel function is used when we have linearly separable classes. RBF is used when we have non-linearly separable classes. Sigmoid is mainly used for binary classification. And lastly, polynomial is used when we have polynomial features. Let's say I have a feature x. I take x square, x cube. These are the polynomial features of your variable x. What is the advantage of SVM? It's fairly robust and it can handle nonlinear relationships. The Python implementation for the regression and classification of support vector classifier is given here. Please remember that there are hyperparameters that we need to tune. The two important hyperparameters for this include the kernel function and the penalty. Our next technique is decision tree. As with SVM, decision tree can also build classification or regression models. The uniqueness is that the models are built in a form of a tree structure. This can be considered as breaking the data and making decisions on the basis of a series of questions. Entropy and information gain are used to build the decision tree. What are the advantages of this technique? It's easy to interpret. No scaling of features is needed, and it works well on large data sets, and it can also learn complex relationships. The only disadvantage is it has lot of hyperparameters to be tuned and also at times lead to overfitting. But this overfitting can be controlled by pruning the tree. You see the classification and the regression model for the decision tree. Now we come to another important set of technique called as ensemble machine learning techniques. So ensemble means combining. So what are we combining? We are combining different classifiers to build a meta classifier. This meta classifier will have a better performance as compared to individual classifiers. Now the way in which the meta classifier is built decides the ensemble technique, which includes bagging, also called as bootstrap aggregation, and boosting. If we look at this picture, we can get an idea of what is the difference between a single classifier, a bagging model, and a boosting model. A single classifier works on a single data set. But if you look at a bagging model, it will make the subsets of the data set and it will create different models with respect to the subsets that are there. And this will be done in parallel. Whereas if we look at the boosting, the subsets will be created. For the first subset, a model will be built. From the model output, the input will be given to the second subset and a consecutive model will be built. So boosting will involve sequential building of the models for the different subsets that are there. Let's understand bagging in little more detail. Bagging, as I told you, it combines multiple learners so that we can reduce the variance of estimates. For example, random forest. It's nothing but it's a type of a decision tree where instead of one decision tree, we are building n decision trees. And these decision trees are built on the subsets that are randomly created from our data set. So the trees are trained on the random subsets of data and the voting is done for the final prediction. So when we have, lots of models and then we combine those models to build one more model, the accuracy of the consecutive model is better. And that is why bagging is an important approach for machine learning. Now, let's come to boosting. As I already mentioned, boosting involves iteratively combining weak learners to build a strong learner. And why are we doing this? So that we can predict our output more accurately. Three types of boosting methods are there, which are based on how the aggregation of weak learners happen. These include ADA boost, XG boost, and gradient boost. So please remember, if there is a confusion that when to use bagging model and when to use a boosting model. So bagging model is used on weak learners that exhibit high variance and low bias, whereas boosting methods leverage when low variance and high bias is observed. So this can be a guiding line to which model to select for your ensemble learning techniques. Now, once we have built the models, we have to evaluate the performance of these models. So what happens when we are trying to build a supervised learning model? We have our input data set. We divide our input data set into training data and testing data. The split ratio can vary. The ideal 70-30, 70% of the data for your training and 30% for your testing. It can change 80-20, 90-10, 60-40. So modelers try different combinations to come up with the best model. When we are building a supervised model, we use the training data to make our model learn the patterns. Once the model is built using our training data, we need to check or evaluate the performance of the model. So what do? We divided our data set into training and test. So we take the test data set and we give it to the model, and we determine the performance of the model on basis of the output that we obtain for the test data set. Please remember, the test data set is a part of the labeled data set. So we have the actual output and the model will give us the predicted output. Now, depending upon whether it is a classification model or it's a regression based model, the predicted output will change. For the classification model, the prediction output will be in terms of the desired class, and your actual output will also be the class. But if we look in terms of a regression model, the desired output will be in form of a real number. We also have the actual output in form of the real number. So when I say that we are evaluating the performance, what are we looking? In classification, we are looking whether the class for the actual and the predicted output are same or not. If they belong to the same class, that means our model has predicted accurately. But if both of them don't belong to the same class, then we say that the model has not predicted correctly. So there are 5 matrices that are used to determine the classification accuracy, that include accuracy overall, precision, recall, F1 score, and confusion matrix. If we look at the regression based technique, I told you we have the actual output in form of a number and we have a predicted output or the forecasted output in the form of a number. Let's say I'm looking at the temperature forecast. Today's actual temperature is 30 degrees and the forecasted is 29. So if I look at what is the error, it is nothing but the difference that is there. So here we are looking in terms of the difference or the variance that is there from your actual to what is predicted. So the matrices that are used for the same include root mean square error, mean absolute error, R square error, and adjusted R square values.